Hi everyone, welcome to this video on Rutherford's model, lesson 3 of the atomic structure and periodic table unit. This is, a classic lesson, and in terms of exams, it appears both in chemistry and physics. It's absolutely foundational, really important, and every science teacher kind of knows it, and yet I think it's really difficult to teach, or a lot of science teachers find it really difficult to teach. And I hope if you've watched any of these other videos that I've been doing, hopefully it's beginning to make a little bit more sense how we'll teach a lesson like this. Because I think the reason students find it difficult and teachers find it difficult to teach is because they're not working within a model that Rutherford's model and the gold foil experiment fit into. Whereas what you're going to see today is we introduced this model for how scientific knowledge develops from lesson 1 of year 7 in the GLT curriculum. And what I hope you'll find in this lesson is everything that we've been doing up until then. So all of those lessons that we did on what is light and fields and Pasteur's germ theory and phlogiston and concentration of mass and all of that stuff, because we've been using this guess, deduce, check model, this lesson will just seem like another lesson, and hopefully that's going to help students understand it a lot better. And that's not just for the sake of exams, that's because it's kind of nice for students to understand what it is that scientists are doing, and you know how that really important part of their intellectual inheritance came about. Anyway, that's enough introduction. Let's begin by just reminding students of our model of scientific knowledge. And again, if you have different words for this, that's fine, but I like to call it guess, deduce, check. And if you haven't seen the Feynman video in which he uses similar language, it's worth watching Feynman on the scientific method. So let's recap on what we did in the last lesson. So we got to Thomson, and he had done the cathode ray tube experiment. He'd found that there's these tiny little particles called electrons, and what he said was, well, I don't really know where they are, so I'm just going to assume that you've got this ball of positive charge and these electrons scattered randomly within it. I've got a new pen, so there we go, I know how to get it ready. So we've got these electrons scattered randomly within a ball of positive charge. So you might want to label that and annotate it, but that was covered in the previous lesson. What I think is worth emphasizing here is that the way Thomson visualized the atom in his plum pudding model was that mass and charge were distributed evenly. And what we mean by that, and we really want to, we're going to test students' thinking on that later on in this lesson, but what we mean by that is that the mass is spread out evenly throughout the atom. So there's no parts where there's lots of mass and other parts where there's less mass. It's just a kind of continuous ball of matter with these electrons scattered randomly within it. So then we come to the gold foil experiment. So again, a simple sketch is going to do here. So you can talk through what Geiger and Marsden did, and it's important that I think they kind of have some sense of what's going on. So you've got this what's called an emitter here, and they won't have come across this probably. Some of them might have done, but they won't have come across it in the curriculum. This was emitting something called alpha particles. You don't need to worry too much about those later. Maybe when you're coming back to revise in year 11, after you've done alpha particles and alpha radiation in physics, you can kind of dwell on this a bit further. But for now, you can just say they're these super high energy positive particles. So what I'm going to do is show these alpha particles, very tiny, even tinier than atoms, being emitted. And you might want to put here that they are high energy and positive, and that's going to be important later on. Now, what Geiger and Marsden did is fire those at a sheet of gold foil. So by this point, we're kind of almost 100 years after Dalton has suggested everything is made of particles. So we're hopefully pretty happy with the idea that solid things are lots of particles in that fixed lattice. There's a nice regular arrangement. Now, what we need to emphasize to students here is these are like bullets. These are super, super high energy particles being fired. So what you'd expect to happen if this model was true is that all of these would just blast straight through. So you'd get a kind of blast zone here, and these alpha particles would just carry on straight through. So if you were to put a detector here like this, I'll label that as a detector, what you'd expect is that 100% of the alpha particles that you fired out ended up at this detector right behind the gold foil, because they're all just going to blast straight through. And again, I'm sure you've heard metaphors about this in various resources. So I think I'd be right in saying Rutherford described it as firing a cannonball at a piece of tissue paper. I often talk about firing a bullet from a gun at a blueberry muffin. Because that mass and charge are distributed evenly, there's no kind of very dense bits and no empty bits. What you'd expect is that all these alpha particles just blast straight through. So they're all detected there. So this is where it gets interesting, isn't it? Because this is where, when we actually look at what Geiger and Marsden did, so if we draw the gold foil here, and I've just realised perhaps I should have labelled that. So I'll do that in the previous one. You might want to label this as the gold foil. If we've got our gold foil here and our alpha particles are being fired out here, so they expected them all to just go straight through, but what actually happened was, well, okay, they had a detector here. I've drawn that a different shape for some reason, I'm not sure why. They had a detector here, and most of the alpha particles were detected over here. But for whatever reason, they decided they'd try putting the detector here too, and maybe up here too, at an angle. And what they found was, some of them, most of them went straight through, that's what we said before, but some of them seemed to be deflected, like this. Only a small number, not loads and loads, but a small number seemed to go through like that. They were deflected. And some of them even seemed to bounce back, because when Geiger and Marsden put detectors here, let's put detector again just so students know what we're talking about, what they found was some of them seemed to go into this gold foil and then bounce off and end up at to here like this. And this won't be news to you, but I'm sure it will be news to the students. Now, again, if you've ever taught this lesson before, you'll be aware students kind of look at you when you're talking about this and go, okay, so what? But what we want to do then is say, well, okay, we've got 3 observations here, and the genius of Rutherford was to say, because of these observations, we're going to need a new guess as to what atoms actually look like. So what I like to do with students, I'm going to do this in a different colour. It doesn't really matter what order you do them in, so I'm just going to do 1. I'm going to label the observations 1 for the deflection observation, 2 for the most going straight through, and 3 for the fact that a small number bounce back. Doesn't really matter what order you do it in. But what you want to say to students is, well, what Rutherford realised is, okay, the fact that some of them are being deflected, that means we know these alpha particles are positive. So he's thinking, well, hang on. Maybe then, the fact that some of them are positive, maybe there's some sort of repulsion going on with something inside the atom. Positive and positive repel. So he's thinking there must be a region inside the atom where there's something positive. Now, the fact that a very small number of them bounce back, and maybe this is the easiest observation to start with, even though I've put it as number 3, he said the only way this could be possible is if mass and charge are not evenly distributed. The only way this would be possible, and I should put here, we're going to need a new guess, because what we'd expect to happen isn't what we saw. So when we come up with a new guess, what students need to realise is that Rutherford's guess was based on what he observed in the gold foil experiment. So, sorry, recapping. The fact that some of them bounced back, he realised this meant there must be something very, very, very tiny, which he assumed was in the centre of the atom, and that's called the nucleus. And you might want to label this, or you might want to, let me zoom out a bit so this is all visible. You might want to label it, or you might want to leave that for students to do when they're doing their deliberate practice. But I'm just going to add a label here. The fact that some of them bounced back made him think, this nucleus must be super, super dense. All of the mass of the atom must be concentrated in this very tiny area. That's the only possible way this very small number of alpha particles could have bounced back. Because they're so high energy, they would have had to meet something incredibly dense in order to bounce back. Otherwise, it makes no sense whatsoever. Then we come to this one. So I labelled this as number one, but it's probably the second one, the second observation to come to. The fact that some of them deflected meant that those alpha particles that went kind of near without actually hitting the nucleus, they were the ones that got deflected. This is what he reasoned. So that nucleus must have a positive charge. But remember, we knew from Thomson's work that there's all these electrons scattered around somewhere. We didn't really know where at that time in the atom. So Rutherford kind of said, well, I guess they're somewhere around the outside. Now, I tend to draw this as a bit of a random kind of cloud because it was only when we got to Bohr that we got these ideas, this idea of kind of energy levels, shells, whatever. So I just kind of have them around the outside. But then I do, just so students know that we're talking about the same thing, I draw a circle around here. So instead of being this ball of positive charge with mass all over it, you've got the atom, which is, you can still imagine it inside a kind of sphere, but what that is just a load of electrons floating about, a very dense positive nucleus in the middle, even if my diagram doesn't look like it's in the middle. And then the last point here is he said, well, look, most of them went straight through. That kind of agrees with the fact that most of this is just empty space. We might want to add a label here that most of an atom is just empty space. And I think what's really important for students having understanding of this topic, the way you can really test their understanding is how did he get from these three observations to this model? And if they can do that, then you can be confident they've got a pretty solid understanding of what's going on here. Now, the last thing that you might want to talk about is, well, hang on, let's just rewind the tape here. So I'm sitting at a desk here. This seems pretty solid to me. But what Rutherford is telling us is that actually, if you were to zoom in and look at the atoms inside a solid table or my own body, for example, actually, most of those atoms are just completely empty space, even the most solid thing in the world that you can imagine. That is a deeply, deeply counterintuitive idea that if students aren't shocked by that, that probably means they've not understood it. And it's one to really focus on with your classes, is to say, well, this is what science does. It allows us to come up with these deeply counterintuitive conclusions that actually give a better explanation of what's going on, for example, in an experiment like this, than our kind of intuitions, which say, well, look, this is solid. If you break that down enough, that must be made of these solid little balls of matter. So this is why I think exam boards think this experiment is so important, because it just provides a really nice illustration of the power of the scientific method, guess, deduce, check, to challenge the way we think about the world and lead us to know more about it than we could possibly do just by relying on intuition. So I hope that video has been useful. We will come on to Bohr and his model in the next video.